In the last lecture, we had introduced the concept of a qubit, which corresponds to the usual classical bits, namely 0 and 1, and we had pointed out that unlike the classical bit, which can at a time take the value either 0 or 1, in case of quantum bits, it can take a linear superposition of that. And in fact, it is this linear superposition which provides the quantum computing with enormous parallel computing capability. What we do today is to extend this concept to multiple qubits. In fact, all that we will do is to talk about 2 qubits cases in somewhat detail, and multiple qubit is just an ordinary extension thereof. So the idea is the following, that if you go to the corresponding classical situation, then your bits are, as you know, 0 0, 0 1, 1 0 and 1 1. Now in this case, the corresponding quantum state is to be regarded as a state which is a direct product of the state, for example in this case, direct product of the state 0 and state 1. This could, for example, refer to the qubit state of 2 different particles or whatever. So therefore, instead of these things, what I have is basically a state like 0 0. This will be the shorthand notation for writing down 0 direct product with 0, and likewise of course 0 1, 1 0, etc. Like in the 1 qubit case, a general state of 2 qubits then will become a linear combination of these things, which let me write it as alpha 0 0 0 0 plus alpha 0 1 0 1 plus alpha 0 alpha 1 0 1 0 and alpha 1 1 1 1. Like in the 1 qubit case, I can normalize this thing such that alpha 0 0 absolute square plus alpha 0 1 absolute square plus alpha 1 0 absolute square plus alpha 1 1 absolute square is equal to 1. Now the question is this, that there is an important way in which the 2 qubit state would differ from a single qubit state, and that is because one can make a measurement of either the first qubit or the second qubit. So if you, for instance, do the measurement on the first qubit and you get a value 0, then it means that the state of the 2 qubit was either this or this, because these are the only 2 states which have 0 in their first position. Now if that happens, then we can say that the probability with which I measure, probability of measuring 0 in the first qubit is obviously given by alpha 0 0 0 0 plus alpha 0 1 0 1. Okay. Well, basically the probability would be given by this square plus this square divided by the whole thing, which we have of course normalized to be equal to 1. The post measurement state of the system would then be this state normalized appropriately, namely this divided by alpha 0 0 square plus alpha 0 1 square, and of course you have to take a square root thereof. Now there is a very important way in which the 2 qubit state, and of course in principle the multi qubit states, they differ from a single qubit state. So we mentioned already that a general state is written like alpha 0 0 0 0 plus alpha 0 1 0 1 plus alpha 1 0 1 0 and alpha 1 1 1 1. Now the point is this, that depending upon the values of these constants alphas which in general are complex, I can obtain different types of states. Consider for example a state like the following. If you refer to the slide, I have given a set of 4 states which, because of their importance in quantum computing, are known as the Bell states. But let me illustrate this with a single situation. So for example, let's talk about a state which is written there as psi plus, which is written as 0 1 plus 1 0 and normalized to divided by square root of 2. Now the question is this, that this state is different from the corresponding single qubit state in the following way, that suppose I make a measurement of the qubit number 1. Now of course I have 2 possibilities, I can either get 0 or get 1 and with equal probability, but notice that when I measure the state 0, the state of the second qubit is automatically determined. If for example measurement of, if first qubit happens to be 1, then this must have been the state from where it came from, and therefore second qubit will then be naturally equal to 0. Now this is very peculiar because I have not really measured the second qubit, I have simply measured the first qubit, but because the first qubit being equal to 1 comes only in that combination, the state of the second qubit is immediately decided, and this thing is known as entanglement. We will have lot more to say about entanglement as we go along in the course. Basically the point is the following, that not all 2 qubit states can be written as a product of 2 single qubit states, and these Bell states that I have given you are examples of that. Now let us translate this into our usual notation for the matrix notation for the qubits. Now look at what is it that we are talking about. See, the basis for a single qubit as we know, the state 0 was 1 0 and state 1 is 0 1. Now I can use this to define a basis for 2 qubits, or for that matter for any number of qubits. So in this notation, the state 0 0, which is a shorthand notation for 0 state direct product with 0, and so therefore I have to simply multiply the matrix 1 0 with 1 0 itself. Now notice this is not a usual matrix multiplication, but it is what we call as the Kronecker multiplication or Kronecker product. Now so the way it happens is, so you multiply first 1 with this whole thing, so you get 1 0, and 0 with this, so you get 0 0. And likewise I will just illustrate one more. For example, if you want 1 0, I know the state 1 is given by 0 1 and state 0 is given by 1 0. So therefore this product is going to be 0 0 1 0. So that provides us a basis of 4. If you look at the slide tells you that there are these states here, 1 3 zeros there, 0 1 0 0, 0 0 1 0, 0 0 0 1, and any 2 qubit state, which in principle is just as I wrote alpha 0 0, alpha 0 1, alpha 1 0 and alpha 1 1, can be written as a linear combination of this basis. Now how many how much of information is there in this type of writing. So firstly, of course, you realize that there are, supposing I have n qubits. So there are 2 to the power n number of complex coefficients I have, because if I have n qubits, then there are 2 to the power n possibilities of the value being either 0 or 1. So that much. But however, as we will see later, that most of such information remain hidden, and when we make a measurement, we will only get n bits of information. The next point that we want to talk about is the process of measurement. Now, the process of measurement is a little interesting thing. You remember that we have been talking about preparing a state in what we have called as the computational basis. A computational basis is basically writing a state as a linear combination of 0 and 1. But as we have seen earlier, that a basis need not be 1 0 and 0 1. For example, for a single qubit state, you could equally well have a basis which is 1 1 normalized to 1 root 2, that is 1 over square root of 2 1 1, and 1 over square root of 2 1 minus 1. And again, any state AB can be written as a linear combination of these two states. Now, so this particular basis which I have talked about is what is known as a computational basis. It's just given a special name, it's called a computational basis. Now, so therefore, in the computational basis, a single qubit state is alpha 0 plus beta 1. Of course, you can always normalize it. And what we know is that in this basis, we can get information about the modulus alpha square and modulus of beta square. And in the last lecture, we have pointed out that if there is a relative phase between them, then a measurement in the computational basis is not going to help. But if you do a measurement in what we call as a diagonal basis, it helps in finding out some information about the relative phase. So having talked about the 1 and 2 qubits, let me now get to the basics of quantum computation. Now before I do that, let me recollect for you that how do you do classical computation. Now remember that in classical computation also, what we have are what we call as the classical logic gates. Now you don't actually have separate gates for depending on what is the number of qubits you have. So basically there are essential components. For example, you could have gates corresponding to OR, AND, NAND, etc. There are some theorems which will tell you that some of those gates are universal, in terms of which you can express all other gates. But the basic point is that you need to define a few elementary gates in order to make an arrangement which can run a computer. Now this is exactly the situation here, excepting there are some other issues. Unlike classical computation, the quantum computation must be performed reversibly, and the corresponding gates that you have, they must perform operations on a state unitarily. So let's now make a mathematical statement out of that. The mathematical statement is that I have, in a typical computer logic flow, I have an input coming in, certain operators work on it, which is what is represented by the logic gates, and I get an output. And in case of classical computation, the inputs are bits, could be for example n bits, and outputs are also bits, could be m bits. Occasionally we require additional registers for doing operations easily, and those will be called as ancillary register, or as is the common practice in quantum computation, we will be calling them ancilla. Now The thing now is this, that what I have instead of classical bit is a quantum state, which we have written in terms of qubits, either single qubit or multiple qubits. Now, when I do an operation on a qubit or qubits, I want the output to be qubit or qubits, that is, a quantum state gets converted into another quantum state, but this operation must follow laws of quantum mechanics, and the operators which are required for this must be unitary operators. If you recall, we define unitary operators as those which satisfy unitary operators. They satisfy u dagger u is equal to the identity. So, we need reversible computation. We have pointed out that normal classical computing is not reversible. You can make them reversible by storing a lot of garbage information, but that is extremely energy inefficient. A quantum computation, on the other hand, has to be reversible. So, let us look at what are the elementary gates that we require for making a quantum computation work. The one point, let me point out, that in classical computation also there is a gate which is reversible, and that is just the NOT gate. The NOT gate is reversible because in NOT gate 0 goes to 1 and 1 goes to 0, and so if you know the output, you can also find out what the corresponding input was. Okay. So, this is, now what is a unitary operator? An unitary operator has this property that it preserves norms, which we have talked about it in earlier lectures. So, basically it preserves the length of a vector. Last time we talked about the representation of a single qubit on a block sphere. So, since all the single qubits have a representation on the block sphere, so if I am converting a single qubit by applying a unitary operator from one state to another state, both these lie on the block sphere, and block sphere, as we have seen, is a sphere of unit radius. So, therefore, the operations correspond to transferring one point on the block sphere to another point, keeping the length constant, which is the radius of the sphere, and so therefore, geometrically they correspond to rigid rotations on the unit sphere, and of course reflections. So, any point can be transformed into any other point by a sequence of operations which are either rotations or reflections or both. Now, if I now go to a matrix representation of these operations, since my input and output both must be of this form, the operator which acts on such a state, giving me a similar looking state, meaning thereby giving me a matrix which has 2 rows and a single column, has to be a 2 by 2 matrix. So, operators which act on this are 2 by 2 matrices. Now, it is fairly straightforward to show that a 2 by 2 matrix in general can be expressed as, this is the general form, e to the power I alpha, alpha is the real, exponential of minus I theta n dot sigma by 2, where sigmas are Pauli vectors having components sigma x, sigma y and sigma z. Theta is a real number, so is alpha, and n is a direction. So basically this is what we want to prove, and in order to prove this, it's fairly straightforward algebra. I would urge you to work it out in detail, but let me tell you some way of doing this. Now remember, I have said U is given by a 2 by 2 matrix. So supposing U has this structure, supposing U is A, B, C, D. Remember, A, B, C, D are complex. So therefore, my U dagger U, you can write this. So remember, the U dagger will have A star, C star, B star, D star. You can just multiply them and realize the following. I can always express a matrix. So a matrix can be always expressed a linear combination of identity matrix sigma x, sigma y and sigma z. So what you do is this, you essentially write down U in terms of this. Remember, sigma x, sigma y, sigma z, I have given this structure several times, but let me repeat again. So I have got I, of course, identity, which is 1 0 0 1, sigma x is 0 1 1 0, sigma y is 0 minus I 0, and sigma z is 0 1 0 0 minus 1. So you write this U in this form and find out what is U dagger. So this is basically a straightforward multiplication. So therefore this expansion will have constant term, which you can trivially see to be mod A square plus mod B square plus mod C square plus mod D square, and terms which are proportional to sigma x, sigma y and sigma z. There are these product terms which will come. For example, there might be a term which is sigma x into sigma y, but by the property of the Pauli matrices, that is nothing but I times sigma z. So convert all these things into that. Now having done that, you can then show easily that this is the way one can write any 2 by 2 matrix. And that sort of tells you what is this. So I am just leaving this as an exercise to you, and you can try it. So with this, let me then go over to 1 qubit gate. So we have already seen that the structure of 1 qubit gates are those which correspond to rotations and reflections on the Bloch sphere. So I will start with, for instance, a NOT gate. Remember that NOT means converting 0 to 1 and 1 to 0, and this is trivially done by the Pauli's X matrix. You can check immediately, this acting on 1 0 gives me 0 1, and this acting on 0 1 gives me 1 0. And this in our notations for a quantum gate will be simply written like this. So this is one of the gates of the single qubit. We have already said that there are other possibilities, because this should be a collection of the rotations and reflections on the Bloch spheres, In the next lecture, we will continue talking about the gates that are possible in 1 qubit and 2 qubit cases, and then carry on to a discussion of quantum circuits.